Hi. Today we will discuss an important class of problems that can be solved using hypothesis testing. Collectively, these problems are called analysis of variance, or ANOVA. And this class is subdivided into several subclasses, and the most important ones are one-way ANOVA and two-way ANOVA. So we will discuss both today. And so what is one-way ANOVA? This is a problem that is quite similar to the problem we have already discussed, that is solved using Student's test or Mann-Whitney-Wilcoxon test. So there we had two samples, and we were interested in mean values of these samples. So are mean values equal or not? And here the question is the same, but we have more than two samples, usually 3, 4, 5, and we are still interested in mean values. Are they equal or not? Here, the special terminology is used. We say that this variable feature, numerical feature we are measuring, is called a response. And a factor is something that can affect the response. So we can say that our samples, several samples we have, they differ in factor. And factor levels are possible values of the factor. For example, we can say that salary of a random person is a response, and the factor is education. And factor levels are primary, secondary, and higher education. So we think, we have a hypothesis that education affects salary. And so we measure, so we have observations, we have salaries of a big number of people, and these people are subdivided into three samples: those who have primary education, those who have secondary education, and those who have higher education. Let's say that K is the number of factor levels, and let's say that we present our observations in a form of a table where columns correspond to the factor levels. So the first column is the sample that corresponds to the first level of the factor, second column corresponds to the second level, and so on. And as you can see, sample sizes may be different. So Nj is sample size of the jth sample, of the sample that corresponds to the jth level of the factor. And capital N is total number of observations, so sample size of the united sample. As in the problem with two samples we have already discussed, here we also consider two cases when the observations, the response, has normal distribution and when it can have any distribution. So let's start with the normal case. But before this, I should explain the mathematical model of observations. So we assume that the response value we are measuring is a sum of three values. The first one is mean value of the response, that is unknown. Then to this mean value, influence of the factor is added, and then influence of all the rest, of all other factors that affect the response, besides the factor we are considering in our problem, we are interested in. So, like, for example, you can say that mean salary, so mu is mean salary in Moscow. And let's say that mean salary in Moscow is, I don't know, 60,000 rubles. So mu is 60,000 rubles. And then tau 1 is influence of primary education. And let us say that primary education gives minus 15,000 to the mean salary. So mean salary for Moscow is 60,000, and mean salary for Muscovites who have primary education is 45,000, is less. And so tau 1 is minus 15,000. Then let's say that secondary education gives minus 2,000 to the mean salary. So mean salary of those who have secondary education is 58,000. And higher education gives plus 20,000 to the mean salary. Mean salary of those who have higher education is thus 70,000. So mean values of the response differ for different factor levels. And tau j is the difference. So the difference between the global mean value of the response and mean value of the response for the specific factor level. And epsilon is influence of all other factors, because we know that salary of a person depends not only on their education, but on, I don't know, on their profession, or on their age, on their, I don't know, some abilities and so on, skills. So this all is described with this epsilon ij. So now let's consider the normal case when we assume that the response is normally distributed, that the response values follow normal distribution, and what is different is the mean value. So for the first factor level, mean value is mu1, for the second is mu2, and so on. In this case, we use Fisher's test, or F-test, to test a hypothesis that the factor has no effect against an alternative that the factor has some effect. And so mathematically we can say that the null hypothesis, the hypothesis that the factor has no effect, can be expressed with this equality, like tau 1 is equal to tau 2. So all taus are zeros. All taus are equal to 0. This means that in this formula, mean value of the response is the same for all factor levels if all taus are zeros. And if at least one of them, of the taus, is not 0, then we say that the factor has some effect, that it affects the response somehow. So what is the test statistic of the Fisher's test? First, we are to calculate the sample means for all the samples we have. So we have a sample for each factor level, and for each of these samples, we are to find the sample mean. So this x bar dot j is the sample mean of the jth sample, of the sample that corresponds to the jth factor level. And then we are to find the global sample mean, or grand sample mean, the sample mean of the united sample. So we add all observations we have and divide by their number by capital M. And the test statistic of this test looks like this. So this expression describes the test statistic. What do we see here? In the numerator of this fraction, we see variation between factor levels. So variation of the response between factor levels. You see, so what is summarized here, we see that we have sum of squares, and what is square? Difference between the mean for the jth factor level and the global mean. So this shows us how mean values for different factor levels differ from each other. So if the difference is big, so then these differences, so this expression in the numerator is big. What we see in the denominator is variation of the response within the factor levels. So we see that we add squared differences of the response values and the mean values for the respective factor level. So the numerator shows us variation of the response between different levels of the factor, and the denominator shows us variation of the response within the same factor level. So what does it mean? It means when the numerator is big enough in comparison with the denominator, this fact is in favor of the alternative hypothesis. So we assume thus that the difference between factor levels is greater than the difference between the variation of the response within factor levels. And if the numerator is small enough, then we can assume that the null hypothesis is true. So this fact is in favor of the null hypothesis, that there is no significant variation between the factor levels. And so this means that as big values of the test statistic are in favor of the alternative hypothesis, this means that we have here right-tailed critical region, and the distribution of the test statistic under null hypothesis is the Fisher's distribution. Fisher distribution with k minus 1 and n minus k degrees of freedom. So we haven't discussed this distribution yet. So this is one of the auxiliary distribution in mathematical statistics, like chi-square distribution and student distribution. So it also has, it doesn't have any physical meaning. It is used in some statistical problems, for example, here. And so to find the border between the acceptance region and the critical region, you are to use the quantile of the Fisher distribution of the level 1 minus alpha. Let's consider the situation when the response is not necessarily normally distributed. In this case, we use Kruskal-Wallis test. So Kruskal-Wallis test is one of the distribution-free tests. So it doesn't matter what distribution our observation have. So the hypothesis this test tests is the same as in previous case. So the null hypothesis is that the factor has no effect, and the alternative is that there is some effect, that the factor has some effect. So this test is rank test, as the Mann-Whitney-Wilcoxon test. So we rank the united sample. We are ranking the united sample. So we totally we have capital N observations, and so all observations are united in the one sample, and they're ranked from 1 to capital N. Then we calculate the mean rank for each of case samples we have, for each of the factor levels. And then we calculate the test statistic. So you see the formula of the test statistic. And so this formula shows us how big is the variation of mean ranks between factor levels. So we see that R bar J is the mean rank for the jth factor level, and n plus 1 over 2 is the global mean. So if all observations are ranked from 1 to capital N, so what is the mean rank? Mean rank is 1 plus 2 plus 3 plus so on plus n divided by n. And so this mean value is n plus 1 over 2. And so this statistic shows us how big is average difference between the mean rank for the jth for different factor levels and the global mean rank. So, as in previous case, here also big values of the test statistic are in favor of the alternative hypothesis, and small values are in favor of the null hypothesis. So, if there is no big variation between the mean ranks for the different samples, this means that probably the factor has no effect. So all the mean ranks for different samples are almost equal, are very, very close to each other, and this is in favor of the null hypothesis. So here we also have, because of this, we also have the right-tailed critical region, and the distribution of the test statistic here is chi-squared distribution with k minus 1 degrees of freedom. So to separate the acceptance region from the critical region, we use the quantile of the chi-squared distribution. So, unlike in previous problem, we have discussed on our previous lecture, here we have also third case. When we say that we suppose that the effect of the factor is directional. So what do I mean saying directional? I mean that, like, for example, we think that we have a hypothesis that education affects a salary of a person. But we think that our hypothesis actually is not that just education has some effect, but we suppose that this effect is directional, that people with secondary education have higher salaries than people with primary education. And people with higher education have higher salaries on average than people with secondary education. So we can order factor levels like primary, secondary, higher, and we think that the response value is increasing. So that mean values for different mean response values for different factor levels can be ordered somehow. And so if our hypothesis is this, so that the factor has directional effect, that it affects the response directionally, then we use John-Heer-Terpstra test, or sometimes it is called John-Heer's test, John-Heer's trend test. Here you see alternative hypothesis is that tau 1 is less or equal than tau 2, and tau 2 is less or equal than tau 3, and so on. And to be mathematically absolutely strict, we are also to add that at least one of these inequalities is to be strict. So if we don't add this, then the null hypothesis and the alternative one will not be mutually exclusive. So how do we test this hypothesis? We introduce a function to compare two numbers. This phi of xi is 1 when x is less than y, 1/2 when x and y are equal, and 0 when x is greater than y. So if this function compares its arguments and returns either 1 or 1/2 or 0, depending on which one is greater, the first one or the second one, the first argument or the second argument. And then we calculate all pairs of the response values we have. So here Let me show you one more time. Here we have capital N response values, and we are to compare every value with all others that are situated to the right in this table. So, for example, x11 is to be compared with x12, x22, x32, and so on. Then x13, x23, x33, and so on. And so it is to be compared with all response values, with all observations that are to the right, that are situated to the right in this table. And so that is what is to be done with all observations. So in practice, this means that you are to compare all possible pairs of the response values. Any pair is to be compared. And if the value that is to the left is less than the value that is to the right, we add 1 to our counter. If they are equal, we add 1/2. And if the value that is to the left is greater than the value that is to the right, we add 0. So we calculate number of such pairs that one observation is. So number of pairs such that first observation is to the left, the second one is to the right, and the first one is less than the second one. So how many pairs, how many such pairs do we have here? And this is J. Capital J is, so this number of such pairs. And then it was proved that this statistic, this random variable J, is asymptotically normal. So this means that if the sample size is big enough, then we can assume that J follows normal distribution. And to make it not just normal but standard normal, we are to standardize J. So we are to find the expected value and the variance of J. And J tilde is standardized J. So it is J minus its expected value divided by the square root of its variance. And so we can assume for big samples that if the null hypothesis is true, then J tilde follows standard normal distribution. And so here we also have right-tailed critical region. And we use quantiles of the standard normal distribution to separate acceptance region from the critical region.